Good morning, Kavita madam. Madam, are you hear me? Kavita madam.
Hello.
Hello.
Hello. Hello. ऐकू येतंय का?
हाँ मैडम.
Hello.
Hello.
लॅग आहे का? टाइम लॅग आहे?
Hello.
हॅलो. टाइम लॅग आहे का?
Hello.
हो बोला. बोला मला ऐकू येतंय.
हाँ ओके. कविता मैडम. हेलो. कविता मैडम. आर यू हियर मी? ओके. So shall we start? Normal sir, shall we start?
Yes. Okay.
Okay sir. Good morning and hearty welcome to this online national workshop on origami, organized by IPSC and Department of Mathematics of Sri Pancham Khimraj Mahavidyala, Sawantwadi. I welcome distinguished resource person Dr. Kavita Sutar from Chennai Mathematical Institute, Chennai. I also welcome Dr. Archana More, who will assisting our resource person in giving demonstrations that will better understanding of the topic.
I welcome our
respected principal Dr. B.L. Bharmal sir, IPSC coordinator Dr. B.N. Hiramani,
and all the
learned participants. Origami is the ancient Japanese art of paper folding. About 100 years ago, people started to get interested in the geometry of paper folding. The questions of interest have been: what angles can be released by paper folding? Are there axioms of paper folding just like there are axioms of Euclidean geometry? How can origami be applied to real life situations to improve existing structures or methods? This workshop will be helpful to explore such type of questions with first-hand paper folding. I am very much thankful to our management for giving us the opportunity of conducting this online national workshop. Also, I am thankful to our respected principal Dr. D.L. Bharmal sir and IPSC coordinator Dr. B.N. Hiramani sir for their valuable guidance and support. I am confident you will enjoy this workshop and enrich yourself by actively involving in all the sessions. I wish all the best in your academic and professional career. I am very much thankful to our staff and technical team for their valuable support.
Taking a step
further,
I request
to our
respected principal
Dr. D.L. Bharmal
to his
deliver his inaugural speech.
Good morning, you all. Good morning, Kavita ma'am. Good morning, Archana ma'am. Our IQSC and Department of Mathematics has organized one-day online national level workshop on origami. I congratulate our IQSC and the Department of Mathematics for organizing the workshop on such important event. Origami, as you know, is the very ancient Japanese art of paper folding, and it is based on the theory of geometry using logic, abstract thinking, and of course, the creativity. These skills are very much useful for sharpening the brain and can be extremely useful to the students of every age, professionals in art, advertising, and also for the planners who need to develop strategies for future. I am pleased to invite Dr. Kavita ma'am, a devoted teacher, researcher, and speaker from Chennai Mathematical Institute, who is expert in this field. She has guided and mentored many students, teachers, researchers, and other professionals. We are fortunate to have Dr. Kavita as a resource person for today's workshop. I am confident you will be enriched by having interaction with her. I wish all the best. Thank you very much.
Thank you, sir, for your best wishes. Then, Then today's resource person, Dr. Kavita Sutar Madam and Archana More Madam. I request to Mrs. S.S. Gadi Madam to introduce our resource person, Dr. Kavita Sutar Madam.
Thank you, sir. On the behalf of Sindhudurga Jilla Shikshan Prasarak Mandal, Shri Pancham Khemraj Mahavidyala Sawantwadi, IQSC and Department of Mathematics, it's my pleasure to introduce and welcome our distinguished resource person, Dr. Kavita Sutar Madam. Dr. Kavita is working as assistant professor at Chennai Mathematical Institute, Chennai. Madam has completed her doctorate degree from Northeastern University, Boston, USA. She has published 4 research articles in reputed journals. She is invited as resource person for many national and international conferences. She has been worked as referee for Journal of Algebra and reviewer of Central Black Math. She has successfully completed 4 research journals. He has been awarded Northeastern University Graduate Research Scholarship and Teaching Assistantship. I request Dr. Kavita Sutar to share her rich experience with all the participants.
Thank you for the wonderful introduction and the invitation. It is a pleasure to be at this workshop and interact with your students. If you will let me share my screen. Okay, yeah. So I can share my screen now. So let me welcome everyone again to this talk on origami geometry. So I'm sure that as kids you have done origami, even as adults, everybody, whenever you have a piece of paper in the hand, you are sort of tempted to do some folding. And I'm sure everybody has folded boats or aeroplanes in their life. Okay, and when you do these folds, you must have suspected that there is some geometry behind it, right? Because you are folding along, you're getting some nice triangle, you're folding, trying to make the edges match with edges, vertices, you make sharp folds. So all these things, when you do, you start suspecting that there is a reason why you want to make these folds precise. And that is true. There is indeed a rich geometry behind all these origami constructions. Okay. So, of course, for a long time, people have suspected this. And origami itself is a very ancient Japanese art. But it was only around in the 20th century or late 19th century when people started suspecting that, there is a structure to the geometry behind origami, and we should probably put it, on a strong foundation. So actually, the honor of writing the first book about origami geometry goes to an Indian author. The name is T. Sundara Rao, okay, who wrote the first book on geometry, okay, as early as 1800. And that book is available on Amazon also, and I will also share the PDF with you later. And it is very written in a very simple language, and the folds are demonstrated through pictures. And you can use it, to enrich your own knowledge as well as help maybe the children in your house or around you to understand these simple.
Madam,
yes.
Madam, sorry to interrupt you. Just one announcement. I request all the participants, if any doubt during the presentation, please send a message in chat box. Then after that, madam will clarify all the queries. Thank you, madam. Please continue.
Okay, thank you. So, as I said, in 1893, T. Sundara Rao wrote this book, and the PDF I will share with you, and it is very readable, and it is very useful for the common people to understand how geometry is involved in origami. Okay, but a more systematic study of it was started in the early 20th century. Okay, one of the most successful results was in 1936 by the Italian mathematician Margherita Belloc. Okay, so whose Belloc fold we will be seeing in the course of this talk. So she wrote a paper about, she was a mathematician, and she found an extremely useful and amazing fold, which is named after her now. Okay. So this is something that she did as a hobby, and she also wrote papers about it. And later, people started getting more and more interested in the applications of origami to various architectural problems, technological problems where you want to sort of compress. So that at the end of this talk, I will show you parts of a small video. Okay, so where you will see the amazing places that origami has been applied to. Okay, so people started feeling the need of getting it onto a more strong mathematical foundation, so that the rules can be written down. And so we know that there are some simple origami techniques we already know. You make certain folds, you get certain shapes. But how does one? There are many problems that can be asked around this simple procedure. Okay, so we will look at some of those questions a bit later. So let me actually begin with my presentation here, okay? And you will see what are the kind of things we will look at. So yeah, so this is what origami means. It's the Japanese art of paper folding, where you don't use any kind of cut or glue or markings on the paper. Okay, the only markings are the ones that you get by folding. Okay. So here are some examples that you might all be aware of, okay, or you must have folded maybe sometime in your life. This is a swan, and there are more things about later we want to see about this swan. Okay. Here's a boat, again something very common. Some fish. Here is a little bit complicated folding procedure. This is a frog, where you see there is one main component and 4 legs. So and you can see things can get even more intricate. Look at this. You might be wondering, how does one even fold something like this? Okay. So indeed, people do fold. This is an example of what is called as modular origami, okay, where you make modules and put them together without gluing. Okay. So you make flaps and pockets, and then you insert the flaps in the pockets, and that is how you get modular origami. This is again an example of modular origami. These are all examples of modular origami. You can make various polygonal shapes using origami. This is an example of a tessellation. So in the end, again, I will show you what a tessellation is. And Professor Archana, who is here, is an expert at these kind of folds. Here are more examples of tessellations, which we will come back to later. Okay. So as I said, if you compare with the history of mathematics, the mathematics of origami is a relatively recent area of research. And the scientists want to understand how to fold different objects in order to minimize the space required. Okay, so when you fold, suppose you have a large object, and can you fold it and make it compact? Okay, this has applications in shipping, for example, okay, or travel, creating travel accessories. Okay. Also in space research, because as you will see in the video, they would want to make objects that fold in a compact way and open when they go into space. So the objective of minimizing the space required is an important one. How particular folds can increase the strength of materials. So this does. So if you look at the applications in civil engineering or architecture, this is one question that is studied there. So how can you fold in such a way that the strength of the material being used is improved, is increased? In medical sciences, protein folding and DNA structure. So it has been, you might be aware already that the protein in our DNA is formed by protein structures which are folded in a particular manner. Okay, and these folds are extremely important. If something goes wrong with these folds, not only with the sequence but also with the folds, if something is wrong, then it can create mutations which are not good for humans or any other creature. Okay. So people have studied people have studied how this protein folds. Okay, and it has very close connections to origami. Okay, so and robot design. So this is also something you will see probably in the video in the end. That so you would want the arm of the robot probably to fold in such a way so that the robot is compact. Okay, and when required, it should open up enough to reach wherever it wants to reach. Okay, so this is just like one very simplistic example. But in robot design also origami is used. And in general, okay, so how do things fold in nature? Okay, you can find nowadays it's very easy to find videos on YouTube where you can. So, for example, the wings of a butterfly, okay, or beetles, they fold. So they have long wings, but they will fold very nicely and compactly. Okay, so this kind of folding can humans also try to imitate in various materials and make use of this fold. Okay, so this is also an active area of research. Okay, so these are the various aspects of origami that are used that are studied in science. So let's begin with some simple fun examples, just as a sort of warm up. Okay, and then we can get into the more technical details. Okay, so for this, what I would like to do is actually share my other screen. So just a moment. I will stop sharing the screen and share another screen here. So I hope you can see this. Um, yeah, here you are. I wonder why it is frozen. Just give me a moment. I think something is not quite right with my camera. Um, Sorry, I'm just trying to get this started. Hmm. Wonder what is wrong. Believe me, I did practice this before, and everything was okay. So now I wonder what is happening. Okay, so now I have to. Um, Archana, can you suggest something here? I'm not able to get to the camera control on Zoom. So this is okay. Now I have to turn the camera around. Sorry, let me just restart this. I'm terribly sorry for this. Yes, I'm trying to flip the camera. That's what I'm doing. So I have left the meeting from that device. Maybe Archana can show you this in the meantime, or because she has it ready actually. I was going to fold it for you, but Archana has this ready. By the time I get this set up, what I want to show you is how triangle, how you can fold a triangle and get the formula for the area of a triangle, as well as that the sum of the angles are 180. Archana, would you please oblige? Hello? I think sharing has been disabled. Yeah, now probably she can share. Well, in any case, if you have a piece of paper with you, okay, so I would suggest that you make a small triangle with it, okay, this kind. If you just make a small triangle, maybe some of you can have your video on, not everybody, so that we can make this a bit more interactive. You can make a triangle, and we want to identify the midpoints of these two sides, okay, which you can do simply by folding one corner over this so that you get the midpoint here. Similarly, okay, there I think Archana has her setup now. This point. Yeah, so you've got the midpoints of these two sides. Yes, Archana, maybe you can. I think you're muted. Okay, so she's muted. Okay, so the midpoint theorem in geometry tells us that I've identified the two midpoints here, and if I fold like this, okay, I will have this parallel to the base. Okay, so that's what I'm doing here. Okay, so I've got this. Now what I'm going to do is I'm going to use this midpoint, okay, and fold this edge over this one like this. Okay. So we've got that. And similarly here, this midpoint, this point, which was the midpoint of this side, now I'm folding like this so that I have this fold here. Okay, so I hope this is visible to everybody. So originally I had this triangle. I took the midpoints of these two sides and I folded a line joining those two midpoints. Then I used this as the reference point and joined folded this edge over this one. That's the first one, and then similarly this side. Okay, so what you see here now is a rectangle. So we had a triangle first, and now we formed a rectangle out of it. Okay, so now what I would like to do is write on this a bit, which is why I was trying to set up that whole thing. But let's see if this works. Okay. So let us look at the angles of this triangle. Okay, so there is an angle here. Let's call it alpha. Okay, so I'm going to write here alpha, which is going to be, see, this alpha is same as what the angle is behind it, right? On the back side also you have the same angle. So I'm going to write this alpha on both sides. Beta for another angle, and then gamma finally. So I've got three angles, alpha, beta, and gamma. Okay, so here's my alpha, beta, and gamma, the third angle here. Okay. Okay, so now look what happens when I fold. When I fold, all these angles come together here. Okay, so I've got my alpha, beta, gamma here. Okay, now what do you think is the sum of these three angles by looking at this picture here? Do they span the whole of this straight angle? Right? So this, if I add up these three angles, beta plus alpha plus gamma, okay, yeah, that's right. That's right. I can see in the chat that people are answering. So exactly. So these three angles, when you add up, it spans this entire 180 degrees. And that's an origami proof of why the sum of the three angles of a triangle is 180. So these three angles were exactly these three angles. Okay. So that's a simple warm-up proof that how you can prove things in geometry using origami. Okay. Now this brings us to one more interesting point here actually. Look, now what we have here is a rectangle, correct? So if we want to see what is the surface area of this triangle, okay, it is the surface area of this rectangle plus the surface area of these three flaps. But these three flaps, when you bring them together, also form a rectangle. So essentially, the surface area of this triangle is the sum of the area of this rectangle plus the area of this rectangle. So twice the area of this same rectangle. Correct? So what you have here is 2 times the area of this rectangle. Okay? And so when you open this, you get your formula for the area of a triangle. Okay? You can calculate for yourself what is the area of this rectangle. Okay, I will leave that to you. So calculate the area of this rectangle, and twice of that is going to be the area of this triangle. So now the question is, what is the area of this rectangle in terms of the base and the height of this triangle? So suppose the base is B and suppose the height is H. Okay, then this is a small simple exercise for you to prove. Okay. All right, so I hope you had fun with that little warm-up exercise in origami. So let me continue sharing my presentation. Okay, so now the plan for the rest of the talk is going to be as follows. So I'm going to talk about the mathematical aspects of paper folding. 3 aspects that I'm going to talk about. The axioms of origami folding. These are known as the Husita-Hattori-Justin axioms. Then I'm going to talk about a couple of theorems. These theorems are nothing but folding procedures which help you generate certain ratios. Sorry, I think we are having... Yeah. So, and then we have, these are the flat folding and crease patterns. This is where a lot of research goes on. Okay, there are some interesting problems in this flat folding and crease pattern. Okay. Then I will briefly, just quickly show you one slide about the various types of origami, which is something you can explore on your own once you know the name. And the various technologies in creating new origami patterns. So again, I will only mention the names. We won't be able to explore these software. But again, this is something that you will be able to explore on your own. I have a lot of material which I will share with you. Okay, the resource material that I use for the talk, as well as some extra stuff that I will share with you, and you can use it. Okay, whoever is interested. All right. So. What are the Husita-Hattori? So first of all, why do we need axioms? Okay, so before we go on to these axioms, remember that the geometry that you learn in school, which was written, so this geometry has been around for a long time, for many centuries, and people in many cultures used the geometry that you learn in school. Okay, but it was Euclid who, in 300 BC, decided or thought that there should be a proper mathematical foundation, a logical foundation, a framework to describe what what are the things that you can do with in geometry. Okay, so there are 2 things. Okay, there is axioms which are self-sufficient, or statements that you need not prove. Those are called axioms or postulates. Okay, self-explanatory statement. And then the other thing is theorems or results, okay, which you can prove using those axioms. Okay, there is a third part in geometry, which is geometric constructions. Okay, this is the area where the ancient cultures were quite advanced in geometric constructions, because they would require to make to construct angles, or measure land, construct right angles, construct hypotenuses for various applications, and they were quite adept at they had invented many methods. Okay, even in ancient Indian history, you will find a lot of methods for these kind of geometric constructions. Okay, so geometric constructions is one more important part of geometry. Okay, so Euclid thought of coming up with this logical foundation, and he wrote the book called Elements, which is now very famous, which has been famous throughout for centuries now. And he was the one who gave the postulates or the axioms for what is now called as Euclidean geometry. Okay, so mathematicians, 20th century mathematicians realized that even for origami to be accepted as a mathematical science, you need a set of axioms. Okay, you need a set of well-defined postulates so that you can derive theorems from those axioms and also know what are the self-explanatory folds. Okay, so in Euclidean geometry you have lines and points, but in origami you will have points and folds instead of lines. Okay? You will be folding along lines, but you will be talking about only folds. Okay? So what are the axioms or what are the self-explanatory statements that sort of explain all kinds of folds in origami? Okay, that was the question. So there were actually, so people, Fujita was the one who first came up with the first 5 axioms. Okay? And then people started to discover even more axioms slowly. Okay, so Hattori and Justin. So it was later this axiom number 7 was found by both of them at different points of time. So their names are also added here. Okay, and axiom 6, which is the Belloc fold, is thanks to Margarita Belloc. Okay, so the one that I mentioned earlier. Okay. So there are these 7 axioms that I would like to now describe to you. And for this purpose, exactly, I was trying to set up my camera earlier, which I had not much success with. So I'm going to give it another try. I want you to be able to see my table here. And I don't know why all the time my camera is being paused. I'm probably going to have have to ask Archana to help me out with this. Archana, do you have your speaker set up now?
Yes, I have.
And do you have your the demonstrating screen?
Yes, I have some papers with me.
I can actually show things on paper here, and maybe you can. Actually, I have some nice paper here to show, and the problem is that I'm not able to access my camera settings on the mobile. Does anybody know how I should do that?
त्या दिवशी झालं होतं ना व्यवस्थित
हो ना, म्हणजे परवा आपण प्रयत्न केला होता तर एकदम नीट झालं होतं.
हो एकदम व्यवस्थित झालं होतं
आणि माहित नाही आता काय झालं. So I did actually go through a dry run to see that things were working fine, and I don't know. Yeah, here I can see some settings. Why is my video being paused during the mobile screen share? This is something I don't know. Am I not allowed? Archana, can you stop sharing your screen maybe?
I'm not sharing my screen. It's just a video is on. Maybe I'll stop.
Oh, you're
my...
not sharing your screen.
No, I'm not sharing. विजय थोड़े से मुझे पेपर लाके देंगे क्या A4 sheets ना.
Okay, so I'm terribly sorry. I don't know why this is not working. I really, went through the trouble of setting it up before the talk, and at the last moment things are not working. Oh, okay, something is here. Okay. Let me just see. Final.
Now we are able to see it. Kavita. Maybe they can pin your that other thing.
You are able to see something? Yeah, maybe you can just pin that screen, please.
Okay, but there is no sharing of screen.
Can you, so if I share the screen, things are going wrong. Okay. But if you pin this.
Okay, ma'am, we will see, but there will be no any screen share at this time.
No, on my second screen, you can see.
I think everybody can pin you because I am able to pin you. So maybe everyone can pin your that screen.
Yeah. So yeah, the thing to do is go to my second screen where you see my hand on the piece of paper.
Okay.
When you take your scroller there, when you take your mouse there,
Okay,
you will see three dots.
I'm going to
right?
pin it.
Yes, pin it, please.
That only means your screen. It will show on your camera. That is your face.
Yeah, it's showing the camera with the hand and the paper.
Okay, ma'am. Now we can see. Okay, ma'am. Thank you.
Yes. Okay. I hope everybody is able to do this. I will give people maybe maybe 20 seconds to pin the screen so that what they are seeing now is this piece of paper and my hand on it. Yeah. So since the screen sharing earlier hasn't worked so well, what you will have to do is, look at this, what I'm doing here, and at the same time, from time to time, you can look at the presentation. Okay. So what I have here is a little piece of paper. Okay, this is transparent paper, so that you can see what I'm doing here. Okay? And I will put it on top of some colored paper so that you can see it clearly. Okay. So now what I want to describe are the Fujita Hattori axiom. Okay. So let's look at the first axiom here. So, just to refresh your minds about the Euclidean axioms, let me remind you what the Euclidean axioms of geometry are. So remember the Euclidean axioms, the first one says that given any 2 points, there exists a line joining them and this line is unique, right? That's what the first axiom says. So now here what I'm going to do is show you this folding axiom, which says that given any 2 points P1 and P2, there is a unique fold that passes through both of them. Okay. So if you look at the pinned screen, okay, suppose I take a point P1 here and another point P2 here. Okay, just any 2 points. What we are saying is that there is always a fold which passes through these 2 points. Okay, so this is what the fold will be. Okay, so here is my fold which passes through the 2 points P1 and P2, and as you suspect, this is absolutely equivalent to Euclid's first algorithm of geometry. Okay, that given any 2 points in a plane, there exists a unique straight line passing through them. Okay, and that straight line, in this case, you can actually just draw by joining. Oh, sorry. So my fold has come at the wrong place here. It should be at this point. Okay, there it is. And so if I just draw a line along this fold or on this fold, this is what Euclid's first algorithm, first axiom, right? Okay, very easy. Okay, let's go to the second one. The second axiom says that given the 2 points P1 and P2, there is a unique fold that places P1 onto P2. Okay, so I have 2 points. There is a unique, that is a single, only one fold which will place P1 on P2. Okay, and let me just find that fold simply by placing P1 on P2. Okay, so let's see, for doing something like this, butter paper is useful because it is transparent and you can see the line below. Okay, so okay, here this is my fold. I have placed P1 on P2. Okay, and as you can all guess, what is this fold going to be? Okay. So this fold, if you like, maybe I have a protractor here, or if I don't, then you can do this construction for yourself. Yeah, I don't have a protractor, but if you do this construction for yourself, you can easily check that this is a 90-degree angle here. Okay, so this is the second axiom, and as you might have guessed, this is equal to the statement in Euclidean geometry that you can always construct the perpendicular bisector of a given line segment. So here my line segment is P1, P2, and I have constructed the perpendicular bisector of that line segment. Right? Okay, so very straightforward again, the second axiom also. Now, the third axiom says that given two lines L1 and L2, okay, so let me take another piece of paper here. And now it's saying that given any two lines L1 and L2, there is a fold that places L1 onto L2. Okay, so clearly we will have two cases. Since we are dealing with two lines here, we will have two cases. One, that the lines are parallel or the lines are intersecting. Okay, so I'm considering first the case that the lines are intersecting. Okay, suppose I have two lines L1 and L2. See, in origami, how this will be used is these two lines will actually be some folds. Okay. Okay, but for understanding purposes, we are taking lines and we want to put the line L1 onto the line L2. Okay, so clearly we are going to we will have two ways of doing this. Either, so this line, this part I will fold onto this part. Okay, and this part of L2 I will fold onto this part of L1. Okay, so here is one way of doing it. Again, the transparent paper is helping me see these lines below it. Okay, so here I have folded. Okay, so here is my fold, so that line L1 has fallen on line L2. Okay, so this L1 fell here and this part of L1 fell on this. Okay, so that is how I have L1 placed on L2. But as you can guess, okay, this is probably not the only way in which you can do this, right? Is there another way in which we can do this? Do I see any chats coming in? There are possibly more ways of doing this, making a fold so that the line L1 falls on the line L2, right? See, what have I got here by doing this fold? Let me draw this line so that the fold becomes more visible. So here is the fold. Okay, this line represents the fold. What is this line? Can you guess? Do you recognize it? Yes, I have a chat there. Okay, so yes, somebody says we can fold it vertically. Yes, of course. So the other way of folding it is you fold it vertically, which means this way, so that again L1 falls on L2 and this part of L1 falls on this part of L2. Okay, that's right. You can fold it vertically. So I'm going to do that. Okay, like this. So I can see that the lines are falling one over the other. Okay. So that's my second fold. So when the two lines are intersecting, there are two folds which will place one line on the other. What are these lines? Did somebody recognize these lines? When I say what this is, then you are going to go, oh yes, of course. What can you say about these two angles and these two? Okay, so these angles are going to be equal, right? If you fold it here, okay, it is the same angle. These are equal angles. Similarly, when we fold it like this, see, this is the same angle on both sides. So this is some beta. Okay, so these lines that you have got here are exactly the angle bisectors. There are two angles formed by these two intersecting lines, and we just folded the angle bisector, right? So the Euclidean equivalent for intersecting lines is constructing angle bisector. Okay. Now the other possibility for two lines is that the two lines do not intersect. Okay. So how can that happen? If the lines are parallel. Okay. So I have these L1 and L2 set of parallel lines. Okay. Now if I fold one line onto the other, what am I going to get? What is this fold? So I folded one line on top of the other. What does this fold give me? It is a third parallel line halfway from L1 to L2. Right? This distance is same as this distance, as can be seen from this fold. It is exactly this distance. Okay. So the two possibilities in this case are that you have intersecting lines in which you construct angle bisectors and parallel lines in which you construct a third parallel line between the given lines. Okay. And what is the Euclidean equivalent of this? Okay, the Euclidean equivalent is simply that given two lines L1 and L2, the two angle bisectors or one central parallel line, depending on which case we are in, can be constructed. Okay, that is the Euclidean equivalent of this third axiom. Okay, now let's. I hope. Are there any questions, by the way? I will stop from time to time to ask if you have questions, and then we can go on. All right. So if there are no questions, let's move on to the fourth one. Okay. So it says, okay, let me take another piece of paper here. So in this case, you're given a point P1 and a line L1. Okay. And then you're saying that there is a unique fold which is perpendicular to L1 and passes to the point P1. Okay. So here is my point P1, let's say, and let's say this is my line L1. Okay. Then there is a unique fold perpendicular to L1 that passes to the point P1. So I want to get a fold that passes through P1 and is perpendicular to this line. So how can I get that? Any guesses here? Would anybody like to guess? Okay, so in interest of time, let me just show you. So I just need to construct a fold that places the line L1 over itself and passes through the point P1. Okay, so let me do that. So I'm going to be careful. I'm going to make sure that the fold passes through P and the line is placed over itself. Okay, that's my fold. Clearly, this is a unique fold. There would be no other fold that would place the line L1 over itself. Okay, so this is the perpendicular from P1 to the line L1, unique. Okay, How do you know that this is going to be perpendicular? Well, one way of knowing it is that what you have done is you have simply reflected all the points on this line across this to this. By folding, you have done a reflection. Okay, so that is a sort of quick proof of the fact that this is going to be 90 degrees. Okay, or that's one way of seeing it. Now everybody knows what is the Euclidean equivalent of this, right? I'm sure everybody knows this. Okay, that you can construct a unique, given any point outside the line, you can construct a unique perpendicular from that point to the line. Okay, in geometry, what you need to do is a compass construction, right? So what you will do is you will construct these equal, you will take a distance on the compass and then construct this point P, correct? Or the other way, you are given the point P and then you will construct these two. Okay, and then the midpoint of that will be this. So this is how you do it in Euclidean geometry. In origami, well, you just construct this fold. Okay, all right. So that's the fourth axiom. Now we can move on to the fifth axiom, which says that given 2 points P1 and P2 and a line L, there is a fold that places P1 onto L and passes through P2. Okay, so now in this we have to be a little bit careful. Okay, so here I have 2 points P1 and P2. So let this be my line L. Okay, this is my point P1, and suppose this is my point P2. Okay, so here also we are going to have cases depending on how close or far this P1 and P2 are. Okay, these relative distances between P1, P2, and L. Okay, okay. So for now, let me look at this simple case. Okay, so what I want to do is I want to find a fold that places P1 onto L and passes P2. Okay, so with origami, this is nothing difficult. Okay, so I just may have to make sure that the fold passes through P2 and it places P1 on the line L. Okay, so I have to have a fold that passes through this point and places. So I have to do some moving around, and I will place this point here, okay, on the line. Is it passing through this? Here, this is P2. Then I move this around a bit and I get the fold. Yeah, that's my fold. Okay, what this fold has done is, first of all, it passes through the point P2. Second of all, it places the point P1 on the line, given line. Okay, so that is my fold. Okay, is this the only fold that I will get, or do you think there are some other folds also that one might get? Okay, so let me see here, right? My fold has to be a bit precise. Yeah, would there be any other way of doing this? What if instead of starting to move on this side, okay, I had started to move on the other side? Okay, I could also have moved this way. Okay, I hope you can see this. I can move this way and look, one more fold. P1 is again on this line below and the fold is passing through P2. So I've got two folds here. Okay, two folds, both of which are passing through P2. Okay, so when we had this fold, let's see where P1 fell. P1 fell at this point. Okay, so I'm just going to mark it for. So this was where P1 fell. Okay, and for when we did the other fold, see, this is where P2 fell. P1 fell at the other fold. Okay, these two lines. Sorry, these 2 points. So here. Okay, so I got these two folds, and these are exactly the points at which P1 fell after this fold. Okay, now in case you have a compass and pencil and you're also trying to do this, And maybe you can even guess this, right? What am I going to show you? If I place the point here and the pencil here, so I'm taking the radius to be the distance between P1 and P2. And look, what happens? This is the point where the circle crosses the given line, and this is the second point where the circle crosses the given line. Okay, so I have this circle which I'm not, drawing very dark because there are too many things here. But okay, but the point is that this circle is passing through exactly these 2 points. Correct? So these 2 points on the line are exactly the points where the circle centered at P2 and radius P1, P2 intersects the line L. Now you can guess. So I had told you in the beginning, there will be cases here, right? So this is one of the cases where this circle intersects the line in 2 points. Now can you guess what the other cases will be? There will be more cases here, right? Any guesses? Quick guesses? How many more cases should I look at? Come on, come on. I gave you, I showed you. So, it should be clear now. What that this circle is passing through this, intersecting this line in 2 points. That is one case. What are the other cases that can happen? If typing is taking too much time, maybe you can just tell me. Somebody can just quickly say it if it has struck you. What are the possible relations between a circle and a line? One, I showed you that the circle intersects the line in 2 points. What else can happen? Okay. The other case, of course, that's very good. Thank you. I don't know who gave that answer, but thank you. Okay, so Amruta. Yes, Amruta. Thank you. So it touches the line in 1 point. Okay. So the placement of the points and the line is such that the distance between P1 and P2 is same as the distance between the tangent from P2 to the line L. Okay. So here is P2. Here is P1. Okay. Now to make things simpler for my construction, okay, I'm going to first draw the circle and then demonstrate the line. Okay. So here, suppose I have a line here. Suppose this is my line. Okay. So now there is only one way in which we can fold through P2 and place P1 over this circle, because there is exactly 1 point where the circle touches this line, okay, which is right at the point where it is tangent. Okay. So you can see through this fold, it's here, right here, okay, which was the point of tangency. Okay. So this is the second case where you can have, so 2 intersections I showed you, then there is 1 intersection, okay, and finally there is 0 intersections. There is no intersection. So the no intersection case will happen if instead of looking at this line, I'm looking at a line which is farther. Okay, so suppose this is my line L1 and now I have a line L2. Now if I want, so P1 and P2 here and I want to place P1 on the line L2 and have a fold that passes through P2, well, you can give it a try. Okay, you want to pass through P2, so you definitely want the fold here. But now, no matter how you turn this point around, okay, P1. See, the point is that this P1 traverses the circle. Okay, since the point P2 is fixed. Okay, so it's not going to happen. This point P1 is never going to lie on the line L2. Okay, so we have these 3 cases. Okay, so I hope you appreciated this agreement. Okay, And the Euclidean equivalent is simply these cases of line and circle intersection. Okay. So this is the axiom 5. Now, before we go on to axiom 6, there is something interesting that I would like to show you, okay, which is closely connected to the 6th axiom that we will talk about. Okay, so let me show you. Now we are going to think about parabolas. Okay, so you have already looked at lines and circles. So now let's think parabola. So there is a way of getting a parabola by folding. Okay, so remember what are the parts of a parabola? You have the focus and the directrix. And what can you define a parabola as? You can define a parabola as the locus of points that are equidistant from the focus and directrix, right? Equidistant from this fixed point and a fixed line, right? That is the definition of a parabola. Let's just use that definition, okay, and look at this. Okay, so you're able to see my pinned screen, right? So because that is where I'm going to demonstrate this. So let me bring up my pen. So here is my point P, which is this fixed point. Okay. And now for ease of folding, what I'm going to do is I'm going to take the fixed line to be the lower edge of this square piece of paper. Okay. Now, if you have a square piece of paper with you, I would suggest that you do this exercise with me because it's extremely interesting and you will have something nice with you. Okay. So you have this point P here and you have this lower line. What I'm going to do is try and construct a parabola whose focus is P and directrix is this lower edge. Okay. Now, if I follow the definition, okay, I want to look at the locus of all points equidistant from P and points on this line. So let me start with some points on this line. Okay. So suppose I start with this endpoint of the line. Okay, I hope you can see it. This endpoint here. Okay, corner point. Okay, lower left corner point. That's on this edge. So it's on the line. Now that corner point I'm going to fold up right to P. Okay. So if I do this folding, okay, if I fold that corner to P, the fold that I get here, okay, or this corresponding line, makes sure that the distance, this distance up to the line and this distance is the same. Okay. So if I actually draw the line that corresponds to this fold, that is going to look like this. Okay. Yeah, that line is my fold. Okay. And now this point on this line is equidistant from both this point in the corner and okay. So here, this point is equidistant. Now let me take another. So you can make folds for each point on this lower edge. Okay. For demonstration purposes, I've chosen two more points. Okay. So let me take this point here. I hope you can see it. So this point here. Okay. Now this point I'm going to fold up to P. Okay. So here, this point I should hold and put it on P. Okay. And then construct the corresponding fold. Okay. Is everybody able to do it? You take a point on the edge, some other point now, not the corner point, but just some other point on the edge. Okay. And then that point you bring up to P, hold it tight, and then fold this. Okay, create this fold. So this way I have created a fold, and if I sort of mark it out with a pen for visibility, this is what I have. Okay. Remember again that because of our construction, all points on this line are equidistant from both P and this lower point. Okay, the equidistant from P as well as this point. way I have constructed. Now I take another point. Okay. Do the same thing for one more point. Okay. So I'm going to fold that one, create another fold. So for visibility again, I'm going to draw this. Okay. Actually, it is interesting to see what is happening here. Yeah. And now, if you continue doing this for all the points on this edge, okay, on the lower edge, you continue doing this. You continue folding a point on the lower edge. Okay, so this one is there. Then you continue with more points on this lower edge. Then you fold this. Okay, so this is this point here. I folded up this point. Okay, continue. Do more. Fold up another point. Then fold up another one. Okay. So continue. Just continue folding till you reach the other corner of the lower edge. Okay, so I'm going to continue this way till I reach the lower right corner. Okay, so continue and more. And finally, I have this corner. Okay, so in this way, I have folded from all the lower or finitely many points on this lower edge up to the point P. Okay, now you can probably see what I will have here. Okay, so you can, if I had drawn all these, okay, I have a sort of parabola here. Okay, if I collect all these points, okay, which are equidistant, so instead of this point, I should be looking at a point here. Okay, not this point. Although this point is also equidistant, we are interested in the point here. Okay, so take the collection of all these points, this point, okay, all these points. If you take the collection of the locus, okay, is exactly this. Okay, sort of parabola here. You should try and do this fold. Okay. What you will have constructed is a parabola with locus, with focus at P and directrix at this lower edge. Okay, do you enjoy that construction? Are there people here who have seen that construction for the first time, or somebody has seen it before? Is there anyone here who saw this construction before, who's been working on it before? Okay, so I hope that since you haven't seen this before, maybe this is you enjoyed this construction. Okay, so yeah, first time. So a number of people are replying saying the first time. Yeah, I'm very glad that I could show you something new. Okay, so this parabola construction, okay, actually helps us understand the sixth axiom. Okay, by the way, this parabola construction and the sixth axiom are work of the Italian mathematician Margherita Belloc in 1936. Okay, that is when she wrote this paper. Okay, so now let me come to the Belloc fold. Okay, so what the Belloc fold says is that, so remember this parabola construction, don't forget it, okay, because the Belloc fold is based on this parabola construction. So now I'm not going to do the all the folding here, okay, but I will request you to try this on your own. Okay, you don't need a transparent paper for this one, by the way. You can just do it on any simple piece of paper. Okay, so it says that if you have 2 points P1 and P2, okay, P1, P2, okay, and 2 lines L1 and L2. Okay, now these 2 lines can be anywhere. Okay, so I will take Let me take this line L1. Okay. They need not be intersecting, or they need not, maybe they intersect somewhere far away and the point is not there on this piece of paper. Okay, many things, number of things can happen. Okay, but for simplicity, okay, and I don't want to waste time here considering all those things, but for simplicity, I will just take these two. Okay, so I will take L1 and L2. Okay. So what does it say? There is a fold that places P1 onto L1 and P2 onto L2. Okay. The word that I have not written here, but the key word here is simultaneously. Okay. That P1 should fall on L1 and P2 should fall on L2 simultaneously at the same time. One fold that does both these things. Okay. So let's see. I want P1 to fall on L1, P2 to fall on L2, one fold that will do both these things. So what I'm going to do is I'm going to put P1 on L1 first and then move the paper around to sort of put P2 on L2. Okay, so P1 is on L1. Yeah, there it is. I got it in the first go. So I found a fold here. Okay. So now you can see probably because this paper is transparent that P1 is lying on L1 and P2 is lying on L2. Okay. Let me mark out this remarkable fold. Okay. Now, what is remarkable about this fold? Suppose you were constructing a parabola with focus, so with this kind of line and point pairs, we have two constructions, right? We have two parabolas that you could construct. One which has focus P1, directrix L1. The other which has focus P2 and directrix L2. Correct? Now, what can you say about the points on this line? Since P1 folded onto L1 because of this fold, I know that the points of this line are equidistant from both P1 and L1, right? So for example, I know this distance is same as this distance, or this distance is same as this distance, and so on. Okay. So the points on this line are equidistant from both the focus and this direction, right? These are all going to be equal distance. So that's with P1 and L1. Okay. So this also means that this fold lies on, there is, if I construct the parabola with focus P1 and directrix L1, okay, that parabola is going to have points that fall on this line. Okay. Now, the same thing goes for P2 and L2. Because the fold put P2 on L2, the points on this line are equidistant from both P2 and L2. Right? Similarly, I can take P2 on L2. Right. So there are the points on this equidistant from, there is one point, There is one point here which is equidistant from both P2 and L2. Okay. So this was one fold that I constructed. Okay. But what do we know about these points which are equidistant from both P1 and L1 and P2 and, equidistant from these two and equidistant from these two? What it means is that what did we see about parabolas here? When we constructed these folds, okay, these folds were actually all tangent to this parabola, right? You can consider this imaginary parabola here. And when we were doing these folds, okay, what we were getting were tangents to this parabola. Okay, so for example, this fold is tangent here. Okay, if I fold like this, that is tangent here. Okay, if I look at this fold, that fold is tangent somewhere else. Okay, and the collection of all those points actually forms this parabola. It's like I'm looking at all possible tangents and collecting those points and constructing this parabola. Correct? So now what is the significance of this line then? So this line is tangent to both the parabola that passes that has focus P1 and directrix L1, as well as focus P2 and directrix L2. Okay, so this special line is tangent to two parabolas, to both the two parabolas that I have written earlier. Okay, tangent to both parabolas. Okay, so this is the special Belloc fold. Okay, so this is the Belloc fold. Why is this special and why is this interesting? So in general, if you consider parabolas, okay, what are the cases that you can have? If you have two parabolas in general, you can have either one common tangent, okay, this way, or you can have two common tangents this way, okay, or you can have three common tangents this way. Okay. You could also have no common tangent. Okay. So now finding a common tangent to two parabolas has been an interesting problem in mathematics. Okay, and there is no Euclidean geometric construction that will give you this, or that will locate for you the exact tangent to both these. Okay, but origami does it. Okay, with origami, with the simple construction of placing P1 on L1 and P2 on L2 simultaneously, which you saw was so easy, what you have done is constructed a tangent to both these parabolas. Okay, so that is the speciality of the Belloc fold or the axiom 6. Okay, the Euclidean equivalent is the line that is tangent to these two parabolas. Okay, so that is what I was explaining to you. Okay, so I hope I could convey this. All right, how much time do I have? Hello? Okay, so let me just show you the last axiom. Okay, so of the Fujita-Hattori axiom. Hattori just in actually now, but okay. So given one point P and two lines L1 and L2, there is a fold that places P onto L1 and is perpendicular to L2. Okay, so here is my point P, and now I want to have L1 and L2. So L1, maybe L2 here, L1, L2. Okay, so I will have to search around for this fold actually. So let's see. There's a fold that places P onto L1. I want to place P onto L1, but I also want it to be perpendicular to L2. Okay, so which means that L2 has to be placed onto itself. Okay, so this fold is actually going to go beyond my paper. Okay, so I will take a positioning somewhere else. I will take these lines a bit closer. Okay. Yeah. So I want to place L2 on itself and I want to place P on this other line. Okay. So P should fall on the other line and this other line should fall on itself. So here is my fold. Right here. Okay. So if this is the fold that has placed P, if I fold across this, okay, then P will fall on this line L1, okay, and it is also perpendicular to this line L2. So this is the seventh axiom. And the Euclidean equivalent of this is the statement that given a point P and two lines L1 and L2, there is a perpendicular to L2 such that the reflection of P across this perpendicular lies on L1. Okay, if I take the reflection of P across this line, then it is this point on the line L1 here. Okay, this is the reflection of P across this. This is the Euclidean equivalent statement of the seventh axiom. Okay, so I hope you had some fun exploring these axioms. Okay, so I did spend considerable time on these axioms. There were some more interesting things to show you, but yeah, that is why I'm asking how much time I have, so that I can decide what more to show. I think I'm almost out of time. Okay. Hello. So is Professor Sonalkar here?
I think you may have I mean, you don't have time. You just, I don't know where you feel.
So मला जस्ट विचारायचंय की किती वेळ आहे माझा वेळ संपत आलाय का मी अजून एक 5-10 मिनिटं बोलू शकतो?
5-10 मिनिटे मॅडम 5-10 मिनिटे बोलू शकतो तुम्ही कंटिन्यू करू शकता.
ओके 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 ओके
डाउट्स वरती असतील आपण बघू.
हो हो. So yeah, I don't want to. Okay, thank you. So I will definitely give you some 5 minutes to ask questions, but there were a few more interesting things that I wanted to show you. Okay, so these were just the axioms. So now it has been shown that these 7 axioms are actually the set of complete set of axioms. Okay, so that there cannot be any more. Okay, so it requires some understanding of logic to see what it means to have a complete set. But for now, it is enough to know that now there cannot be any more axioms that will be added to these. Okay, so we have a complete set of axioms for origami. Okay, so now what I wanted to show was Hager's theorems. There are 2 or 3 theorems here. Okay, so I'm not going to show you all those now because we are out of time, but I will quickly show you one. Okay, so there is something appearing here. I don't know what this is, but okay. Some lines appearing on the screen here. All right, that's not from me. So Hager's theorems, I will quickly show you the first Hager's theorem because I think it will pique your interest. Okay, and it is something that you can also try. So as I said, I will share with you the resources. Okay, so with those resources, you will be able to try these axioms for yourself. Okay, so here again, we go with this piece of paper. Okay, what I'm going to do is for Hager's axiom. Okay, I'll take a fresh piece of paper. Okay, so that the markings are not already there. So here is my fresh piece of paper. I hope you can see it, and you can sort of follow this construction with me. Okay, I think the camera has turned. Let me see if I can get it back. Okay. No, it won't turn horizontal. Yeah, there it is. Okay. So now, if you can see this piece of paper, okay, what I'm going to do is quickly show you Hager's first theorem. Okay. Well, the point of showing you these theorems is the following. Okay, so Hager is not even a mathematician; he's a biologist. Okay, a Japanese biologist who did paper folding in his free time. Okay, and he discovered these theorems. So discovering theorems is something that any one of you can do. You don't really have to be a specialist in any of these subjects to discover these interesting results about origami. Okay, so this demonstrates this fact. So here he discovered these theorems mostly when he was traveling in a train to work. Okay, from home to work, he discovered this. So this is what I want to do. Okay, I want to mark the halfway point on this edge. Okay, so this is half. Okay, now the thing to do is I want to make a fold. Okay, which passes through this point. Let me mark it with a pencil. this point. So I want to make a fold passing through this point and which will take this vertex to the opposite edge. Okay. So let's see if I can show you this. So here it is. I want to make this fold through the point and put this corner on the opposite edge. Okay. So let me try this. With some work. Looks like it might be possible. Yeah, here. Right. So now I have put this point on the opposite edge. So sorry, this is the second theorem. What am I doing? I want to put the lower corner on this point. Okay, yeah, this is the first theorem. Sorry. So the lower left corner up to the midway point of this edge. Okay, you see this point and you see this lower left corner. You pick up the lower left corner and put it up to this point. Okay, and now you make this fold. This is called Hager's first fold. Okay, or the first theorem fold. Why? What is interesting about this fold? Okay. So let me show you some interesting things. What I want to do now is do some markings on this piece of paper. Okay. So what I want to do is call. So first of all, we know that this was the midway point, right? So this is going to be half. If I say that this is unit length, okay, this is unit length, then this is half and this is half. Okay. Let us call this distance x. Okay, and let us call this distance. So this distance means up to this point, right? This much part of the edge. And this part of the edge from the upper corner up to this point. Okay, this much I am going to call y. Okay, now as soon as you call these x and y, you can unfold this and realize that if the point of this distance is x, then this distance is going to be, well, this is unit distance and this is x, so this is 1 minus x. Right? That is this part folded up here, this distance is 1 minus x. Similarly, on this side, if this much is y, then this remaining part is 1 minus y. Which means this flap here, okay, this piece of the flap here is 1 minus y. Okay. Now what we'll do is, there is also this straight line, correct? This straight line I'll call this distance as b. Okay, this little segment I will call b. Okay. Now let's call this angle here. So this flap has come here. Let's call this angle alpha. Let's call this angle beta. We know that because this is a corner of the paper, we know that this angle here is already 90 degrees. Okay. So this also tells us that alpha plus beta must be 90 degrees. Okay. So now the question is, what are x and y? Okay. So to save time, what I will do is, I will quickly do a derivation of x and y for you. Okay. Because probably this is the first time some of you are seeing it. And I will leave the generalization to you. Okay. So the point of Hager's first theorem, or the point of doing this fold, is that you will see that without using a ruler, which means a marked straight edge. Okay. A ruler means something like this on which you have marking, right? Of course, you could use these markings to measure out these distances. But the point of geometry or origami is to not use something like this with markings or numbers, but try to construct these distances on your own, okay, without any help other than folds. And this is what this is going to do. Okay. So let me give you hints and maybe you will be able to do this by yourself. Okay. So look at what this is x, this is half, this is 90 degree. So in this triangle up here, we know that x square plus 1/2 square is equal to 1 minus x whole squared. Okay. Now, if you solve this for x, what you can guess from this that you will, to solve, when you solve this equation, you'll get a quadratic in x, correct? Which you can solve. So I will leave the exercise to you. Solve this quadratic. What you will get is that x equals 3/8. So this is what this much distance is. Okay. Which will also tell you what is 1 minus x. Okay. If x equals 3/8, then this 1 minus x is going to be 5/8. Okay. So what you have done with this fold is you have folded this side into these two ratios, 3:5. This is the ratio in which you have folded, or you have found the point that divides this part into the ratio 3:5. Okay. So can I leave the rest to you? Here is a pair of similar triangles. This triangle up here, okay, and this triangle here. So that consists of y half and this hypotenuse. Okay. So if you do this, if you realize the similarity between these two triangles, this is a similarity. It is easy to find. Okay. So you will get y over 1/2 is 1/2 over x by similarity. Now you have already found x, so this will tell you that what y is. Okay. So if you solve this, you will get y equals 2/3. Hence, 1 minus y equals 1/3. What does that mean? It means that you have divided this edge into two parts. Okay. So you have 1/3 and 2/3 here. Okay. So one is to, is there something fishy?
That 1 minus y.
Yeah, I think. No. So 1 minus y is not here. Sorry. 1 minus y. See, y is up to here, and 1 minus y is this whole thing actually. Sorry. Yeah, this is 1 minus y. Yeah. So this is 2/3 up to here. Okay. And then the rest of this is 1/3. Okay. So now you have divided this part into 3 equal pieces. Okay, so you did this division without using anything fancy, just one fold, and that is the reason why this fold is interesting. Divided this into different ratios, it divided this side into different ratios. Okay, so you've got two things. Okay, you can get some more by exploring what happens in this small triangle here. Okay, so here if I call this piece as Z, okay, remember this angle is going to be alpha, you can check this. This angle is going to be beta, this side is Z, this side is B, that's what I'm calling it. Okay, and suppose we call this piece as A. Okay, so suppose this piece is A. Okay, again you will be able to show that by similarity x over b is equal to y over a, and z over c is equal to y over 1/2. Okay, where c is this piece here. Okay, whatever this 1 minus, no, whatever I had written here is wrong. This is c. Okay. Oh, I'm sorry, you cannot see it. This piece here, this little flap here. Okay, this is c. Okay, so by similarity you can show this. Okay, and once you have shown this, you will be able to find 24. Okay, and c is 1 over 8. Okay, so this c, this little flap, this distance here is 1/8, and you can check that it's 1/8 by doing repeated half folds, right? Half and then half. Okay, that will also, you can check that this c is actually 1. Okay, all right. So this is you, or what you should try to explore is, now what will happen if Instead of folding it to half, you fold it to some other point. Okay, so this is exercise that you can try. Now do the same logic. Okay, don't fold it half, fold it at other points. Okay, call this k, then this thing will be 1 minus k. And use the same logic and see what ratios you can get. And you can check through, you can look at the resource material correct. Okay. And what you do is, quickly, interesting thing that I could not touch. Okay, maybe some other occasion we will talk about it. But also my the resource material, you can look at it, which is this. Here is where some research problems in origami lie. Okay, which is flat folding and crease patterns. Okay. So you can look at these. Okay. Actually, proper question answer. Okay, proof using folds. Okay, and there are even more research problems. Okay, so this was one part that I did not touch at all. There are other interesting forms of origami like modular origami and origami tessellations, which are very artistic, more artistic than mathematical. And if you like to fold, this is something you should definitely try out. Okay, and finally, there is a lot of technology in creating new origami patterns now. Okay, as you can guess. Okay, a few of these are origamizer. Okay, you can check this out. There is Premaker, and there are many more. Okay, so I have a link here to one of the foremost names in origami today, mathematician and physicist Robert Lang. Okay, so I have a link to his page here. Okay, and on that page you can find a lot of these technologies, a list of software where you can sort of do digital folding. Okay, so or virtual folding, and then see what is the crease pattern. Crease pattern means after you have folded and unfold the paper, whatever you see is called the crease pattern. Okay. So that kind of thing you can do with these softwares also. Okay. So thank you very much for listening. Although I couldn't really, there were some problems with technology. I'm sorry, and I couldn't finish up whatever I had planned. And because of that, you probably missed out on the wonderful proof that Professor Archana would have shown you. But she's you know her, and I'm sure that if you have questions even later, we will be very happy to address those. Okay. And if you want if any of you get interested in this and want us to hold a small, informal session, I and Archana will be very happy to do that with you. Okay. So thank you all for being patient with all the problems that I had here and listening to this talk. I really hope you enjoyed it. And thank you to Professor Vishwas Sonalkar for inviting me to this session. I hope I could, make you feel some interest in the mathematics of origami. Thank you.
Okay. Thank you, Kavita madam, for your lecture on topic origami geometry. Then I will request Ms. Rupali Bandekar madam to give vote of thanks for this session.
On the behalf of Sindhudurga Jilla Shikshan Prasarak Mandal, Shri Pancham Khemraj Mahavidyalaya Sawantwadi, IQAC and Department of Mathematics, I thank our resource person Dr. Kavita Sutar, for sharing her valuable insights on origami geometry. Madam, in her simple language, has effectively delivered the concept of origami and geometry of paper folding. I am very grateful to Madam for giving answers to the following questions. What angles can be realized by paper folding? Are there axioms of paper folding just like there are axioms of Euclidean geometry? How can origami be applied to real life situations to improve existing structures or methods? I am thankful to Dr. Archana Morie for her help in giving demonstrations. Once again, I thanks to Dr. Kavita Sutar for making this session very enriching. Thank you, Madam.
Thank you very much again for inviting me. There is just one more thing that I would like to add is again, I would like to tell the participants and especially the students who are here that Archana and I would both be glad to, have an informal session where we can explore more of these things that I could not explore in the talk today because of, time constraints and some technology considerations. But there are some really interesting things that we would like to show you. And I will share the resources with Professor Sonalkar, who I hope will share it with all of you. There are some very interesting
okay.
videos. Yes.
Yes, I will
Thank
share,
you.
madam.
Yes. Thank you so much.
Okay. Thank you, madam. Thank you.